have been invited to give essentially 4 hours lectures on the topic of dark matter from standard model and beyond, and production mechanism. So if I would have been in Madrid and I could have been giving you this lecture in person, I would have wanted to use a blackboard, which is the way I like to teach theoretical lectures. So I have no blackboard, but I have a tablet. So I will be giving my lectures on the tablet. I hope it will be will be clear enough for you. So yeah, let me begin now. Oh, please stop me at any time when you have questions, and I will be extremely happy if there would be any kind of interaction during the discussion. So my topic was dark matter from the standard model and beyond, and production mechanism. And what I really wanted to do is to have, not really to go through all possible dark matter scenario and so on, but I will essentially pick kind of 2 dark matter scenarios and try to go through the largest number of dark matter mechanism production I can go to. In order to do that, I will essentially give you first the setup within which I'm going to work. So just to begin in general, I think we all have seen lectures of dark matter. So if it's your first lecture on dark matter, I hope it will be introductory enough, but I will go fast on this. So most of the lecture or the talks you will see on dark matter will always begin with the typical property we expect for the dark matter. And the dark matter itself, we usually tell you that it is a particle, or at least this is the assumption I will do here. And if it's a particle, it essentially shouldn't be dark matter, a particle from the standard model. You usually need to go beyond the standard model. So today I will actually essentially begin with, looking a bit at the standard model, and look at what would be the possible candidate for dark matter, and essentially, re-understand why we need to go beyond the standard model. The second thing you are usually said about dark matter is that it should be neutral. And I think here we need to be very clear about what we mean by neutral. We need that we want that the charge of the dark matter under U1 electromagnetism is equal to 0. Okay, because dark matter can be charged under some gauge group, and in particular, if you just think of the gauge group of the standard model, it could have electroweak interaction, for example. Then the third element that is given to you usually is that it should be at least stable enough for us to have been able to say that there should be dark matter around. So usually you are told that essentially dark matter should be massive in order to account for the structure as they are today. I think someone has to cut the microphone.
You're muted, Laura.
Laura, are you there? We don't hear you now.
Do you hear me?
Yes, now yes.
So you don't hear me since when?
Well, just 30 seconds, no more than that.
Okay, good.
No problem.
Okay, very good. So I was talking about the standard model. So maybe, and I was talking about the gauge group of the standard model. So I guess I will tell many things today that many people know, but just to remind you and maybe to fix the notation or whatever, let me just remind you what is the standard model gauge group. So you have SU3 color times SU2 left cross U1 hypercharge. Okay, so this is a standard model gauge group. So SU3 color are for strong interaction, and SU2 cross U1 hypercharge is for weak electromagnetic interaction. It's the Glashow-Weinberg-Salam model. And after spontaneous symmetry breaking, when the Higgs particle takes a VAV, you essentially break this standard model gauge group to SU3 color times U1Q for U1 electromagnetism. So when we say that dark matter should be neutral, we need dark matter to be neutral under U1 electromagnetism. And so I will just flash you essentially what are the charges of the different particles of the standard model and how we put them together into, for example, doublet of the standard, the doublets. So these are SU2 left, okay, doublets, for example, for left-handed leptons. Into the SU2 left doublet, you have neutrino left and lepton left. So leptons, they are singlet under SU3 color. They're doublet under SU2 left, and they actually have a hypercharge. When you combine the isospin values with the hypercharge, you get the value of the charge under U1 electromagnetism. And this is how you end up with a charge 0 for the neutrino and -1 for the left-handed leptons, even though they are in the same doublet, they have different charges under U1, okay? You can, I mean, by constructing the standard model, and it depends a bit how you are going to write, you are going to decide, for example, how you put the standard model Higgs, how do you put the neutral particle, but essentially once you have fixed that, you can decide, I mean, precise what are the charges of your different particle under U1 hypercharge, and in order to construct Lagrangian that are invariant under the total gauge group, I mean, you are essentially you essentially have to fix all these charges and construct, I mean, everything that goes on with these symmetries. The important point here is that we essentially see that if we want a particle that interacts not with electromagnetism, I mean, we need a neutral particle, so we need a U1Q charge, which is equal to 0. And we also essentially know that we have some difficulties, as you might know, to detect interaction of the dark matter with standard model particles. So we want the dark matter not to interact too strongly with the other particles of the standard model. So for example, I mean, we might not want to have the Higgs particle to be the dark matter, even though it's neutral. Okay, so one particle that we very well know that interacts very weakly with all the particles is the standard model neutrino, okay, which is here, which has charge 0. So this is essentially going to be, let's say, my first candidate for dark matter that I will study around these 4 hours. And maybe just to remind you and fix the notations, let me just go back to, I mean, how does this neutrino interact with the rest of the standard model? So we know that, as I just said, the standard model neutrino is into a lepton doublet, which I have put again here. Sorry. Which I've put again here. And in order to write its interaction with the standard model, and in general, its Lagrangian, I will have a kinetic term, just, I mean, by default, without doing anything. And I mean, just by writing the kinetic term for the lepton doublet, I'm going to introduce the covariant derivative, which, I mean, takes into account both this derivative, partial derivative. Index mu is the Lorentz index, so it goes from 0 to 3. And it also contains gauge bosons into the story. So you have the first term that I have written there in the parentheses is so the derivative. The second one introduced the SU2 left gauge boson, W mu for mu index Lorentz, A goes 1, 2, 3 for the three generators of SU2, which here are the Pauli matrices. Okay, so within all the lecture, this J that I have here will correspond to SU2 left coupling. It will not be a coupling, it's for me the SU2 left gauge coupling. Okay, then we also have hypercharge. So actually, we also have to take into account the insertion of the covariant derivative of the B mu field, which will be the U1 hypercharge gauge boson, and we can actually reshuffle, as you might very well know, reshuffle this kinetic term. We write it in terms of the gauge bosons that interact directly with the particles, so the W mu plus minus, the mass eigenstates, the W plus minus, and the Z boson and the photon. So I will just use A mu for the photon, Z mu for the Z boson. And in going through this process, I introduce the theta Weinberg angle that I will really write usually like cos W of SW, which corresponds to cos theta Weinberg and sin theta Weinberg. Okay. So the goal today is, I hope I will get there, is essentially from these standard model interaction, just by knowing the charges of the neutrino and its interaction with gauge boson, our goal is to explain this plot. So on the y-axis, you see the relic abundance of neutrinos as a function of the masses of the neutrinos. And I mean, if you look at the scale here, okay, GeV, it goes up to 10 to the 5 GeV. So you will tell me, my God, no, I mean, the standard model neutrino, you cannot go up to this very high mass scale. And I fully agree with you. I mean, we have particle experiments constraints from Tritium beta decay that tell you already that the masses of the neutrino should be, the standard model neutrino should essentially be in that region. So at very much lower masses. But I mean, I really want to be very agnostic first and just see in general, let's say we have a particle that has interaction with the standard model through weak interaction. When I say weak interaction here, I say interaction under SU2 left, but actually when we say weak interaction in general, especially when we refer to WIMP, we are much more general than that. It's just interaction of the order of the SU2 left interaction with the gauge coupling, which would be, I mean, a coupling that would be of the order of the gauge coupling that come into the game. But okay, so, I mean, one of my goals today is really to look at standard model neutrino as a possible candidate for dark matter and why, essentially, it cannot account for all the dark matter, because we know very well that, I mean, if we take into account experiments, particle experiments, we know it should be smaller than EV or so. But if we want to look at what it would be, what we need as a mass for this neutrino in order to account for the relic abundance of dark matter today, that is essentially represented by this dashed line here, we would need much higher masses than what is allowed by experiments. So this is one of my goals today for dark matter, possible candidate of dark matter from the standard model. Now, I mean, if I stop there, I will only explain you result, which is a very good mechanism in order to have a nice relation between dark matter relic abundance and its possible signature in gamma rays, which is the topic of this school. But I want also to drive you through other possibilities for getting the relic abundance of dark matter, just to keep in mind that we have a large set of possibilities here, both in masses and in production mechanism in the early universe. So as unfortunately, we will get to the conclusion that the standard model neutrino cannot account for all the dark matter, we will definitively look at other possibilities beyond the standard model. And in order to go beyond the standard model, again, I have thousands of possibilities, and I will not show you these magnificent pictures where you have all the possible candidates wherever in the literature. I'm just going to pick one minimal standard model extension that will allow me to drive you through different mechanisms of the standard model. So, I mean, I'm going to do a certain number of assumptions. And among these assumptions, first, I'm essentially today going to suppose that if I go beyond the standard model for these lectures, I will consider a dark matter candidate that will be a singlet under the standard model gauge group. This will be my first assumption to go beyond the standard model. This means that it will essentially have no charges under SU3 colors, under SU2 left or U1 hypercharge. The second assumption I'm going to do, associated with the fact that dark matter should be stable on the time scale of the age of the universe, I'm going to assume that there is a symmetry that protects my dark matter to decay directly into standard model. So, I mean, essentially what I do not want is to have chi going to standard model, okay? This I do not want. And the, let's say, easiest way and the most used around us is just introducing by hand a Z2 symmetry. So I'm going to assume that I have a Z2 symmetry, which is unbroken until today, and that dark matter is Z2 odd, while every particle of the standard model are Z2 even. Okay, so this is my second assumption. In order to be, I mean, I could, if I just want to discuss the case of the vanilla weakly interacting massive particle, I could very well stop there and give you an example. But I want to go a little bit beyond that today, and hopefully today, if not tomorrow or this afternoon, sorry. But so if I want to go a little bit beyond the vanilla WIMP, I would like to have a little bit more particles in the odd sector of this Z2 symmetry. And in order to stay minimal, I'm going to assume that there is at least one partner, let's say, of dark matter that is Z2 odd. This partner, I might call it the mediator, okay? Sometimes that is going potentially to mediate interaction between the standard model and let's say the dark matter. And why I'm going to assume it's a mediator is because for this lecture, I'm going to suppose that this other particle that is Z2 odd is actually having gauge interaction with the standard model. So I'm going to assume that, I mean, there is dark matter and let's say B, okay, that is Z2 odd. And that is charged under SU2 left cross U1 hypercharge. Okay. And this particle, I will call it, I mean, we will refer it to B because I will call it essentially also the bath particle. The particle that will be connected to the standard model heat path in the early universe, even if my dark matter has interaction so feeble that it cannot interact with the rest of the standard model bath. Okay, and what I'm going to assume essentially is that there exists in my Lagrangian at the very least one interaction term okay, between my bath particle that I just introduced, okay, which is Z2 odd, the dark matter, which is also Z2 odd, so B times chi, essentially. Okay, so this is like a picture, okay? So it's not B times chi for all the possibilities, but the combination of bath particle and the dark matter will be the Z2 even. And so that I can have a third character in this interaction, that would be a standard model particle that I will call A. Okay. So just having decided that this would be my framework, and this is just a choice, so obviously you have many more possibilities, and just to give you an example, you just could very well consider just simply a singlet scalar and have interaction with the Higgs portal, and this would be more than enough, and you essentially don't need another Z2 odd particle in the story. But in order, really to go through all the mechanism, I will focus on this extension of the standard model. And when I'm considering this kind of extension of the standard model, there is the table I have already inserted in this slide, where I give you some kind of classification of the minimal extension of the standard model I could do, and the possible interaction term I can write. So let me rapidly explain you this table. So first, you can say, let's go. I can choose a potential standard model particle here. That would be A. Okay. So my standard model particle could be, let's say, a fermion of the standard model, size Sm, some gauge boson, or in order to work more properly with gauge boson, the field strength tensor associated to one of the gauge boson, or for a scalar, the Higgs particle. Okay, and then then I would like to connect to write a term, Lagrangian term, with dark matter particle that I said that should be completely neutral under all the standard model gauge rule, but I can still choose the spin of the particle, and I'm going. Here I would focus only on scalars and fermions, and once I have decided that, essentially I have only a certain number of possibilities for the spin of my bath particle and its possible representation under SU2 left cross U1 hypercharge. So for example, in these lectures, I will focus on the case where my bath particle is a standard model lepton, actually. My dark matter candidate is a spin 1/2 particle, and my bath particle, the partner of the dark matter in the bath, connected, always connected with the standard model in the bath, will be a scalar. So the interaction term I'm going to consider today, it will typically be this interaction term I have just put a square around a box, which is psi bar standard model times chi times the scalar phi. Now, most of what I'm going to tell you is going to be completely applicable to potential other models that we have here in the list. I propose you, for example, to go to look at our paper where we looked at the phenomenology of feebly interacting massive particles within this classification, but you can find many other references, among others, for example, related to the use of micromegas, for example, where you have a very similar analysis that has been done in the case where you have a scalar dark matter. That would be the singlet under the standard model gauge group. Okay, so this is the framework I'm going to consider when I will go beyond the standard model. In this setup, my goal is to explain you this plot. So remember, if I was considering neutrinos, I had this simple plot where I had the relic abundance of neutrinos as a function of their mass. Essentially, for neutrinos, this is my only freedom, is to choose their mass, because I don't know them. I don't know it exactly. I mean, at the time, at least, where these plots were done, I cannot say up to which point they knew the masses precisely of the neutrinos. But I mean, here I have the interaction of the neutrinos that are fixed with the standard model. They are gauge interaction. I cannot choose them. The reason why I'm playing with this extension of the standard model, and I choose that that extension of the standard model, is because I have essentially the freedom to choose my coupling of interaction with the standard model particle and a given bath particle. So in the case where, as I said, I'm considering a leptophilic dark matter interacting with some lepton. So, I mean, here it looks like an electron, but it could be more general, a lepton. In particular, I'm going to interact with a lepton right, again, to simplify the story and to be able to go through many possible production mechanisms. So in this context, if I look at the Rayleigh abundance of the dark matter here on the y-axis, and I need to fix some parameters in order to be to look at this Rayleigh abundance as a function of a parameter. So here, this plot is made for a mass of dark matter of 150 GeV, and a mass difference between the phi, my bath particle. This is my bath particle. Okay, this is ASM. Okay, so I'm assuming that I have a mass difference with the bath particle of 2 GeV, and I'm coupling the dark matter to a muon in this case. So here you see the Rayleigh abundance of dark matter as a function of the last parameter I have in the story, which is the coupling here in this three-body interaction. Okay, and when I look at for this fixed value of the mass of the dark matter and the mass splitting, I look at the Rayleigh abundance as a function of the coupling of dark matter to all these people. I can see that I have a curve, the blue curve. Okay, and if you look more precisely at the plot, you see that there are a certain number of names here above, and you might recognize some of them, if not all of them. So by considering all the range of coupling, from coupling of the order of, let's say, 1 and 10 to the minus 13 in this Lagrangian above, I'm going to be able to go through different mechanisms of production. And my goal in these 4 hours lectures is to have the opportunity to explain or reintroduce you to all these mechanisms. For the largest value of the coupling we are going to consider, and I hope to get there in details today, we are going to have the usual dark matter freeze out, which is the vanilla WIMP scenario. Okay, then going to a lower value of the dark matter coupling to the mediator and the leptons in this case, I'm going to go through not only freeze out that, I mean, is fixed due to dark matter annihilation directly into the standard model particle, but actually I'm going to be able to consider co-annihilation and actually even to have the possibility to have just the Rayleigh abundance of dark matter fixed by the freeze out of the partner. So I'm going to call this mediator-driven freeze out. Going to even lower value of the coupling, I'm going to be able to go through conversion-driven freeze out or co-scattering freeze out, maybe you have been hearing. Going to even lower value, I will go to freeze-in, and even lower value to super WIMP mechanism. Okay, so hopefully I will have time to go in detail through all these mechanisms. This is at least what I would like to do with you. Are there any questions until now? Any maybe remarks or anything? I would be super happy to hear any of you, just to be sure I'm not talking to nobody.
In the media, in the annihilation diagram, what is the V particle?
This is the in the diagram. Sorry, yes, the V particle is the gauge boson. I didn't want to be precise here, and this is F. So this was a bit cut. And I mean, the goal here is, I mean, was just to flash you the curves for the neutrinos and this beyond the standard model scenario. The idea is that I will go through these two plots and explain you everything that is inside. Okay, so they are kind of summary plots of the mechanism I hope to go through for dark matter in the standard model and beyond. Okay, any other question? No? So if there are no other questions, let me go to really like the theoretical material that we need in order to, I mean, go through all these mechanisms. And I mean, really like the material, I mean, the tool that we are going to use all around is the Boltzmann equation. So Boltzmann equations allow you to essentially describe the evolution of the dark matter, or I mean, generally of the phase space distribution of some species. Okay, so phase space distribution. Sorry, I will write F, which can be a function of position and momenta. And I mean, just to again fix the notation, let me emphasize that I will consider in this lecture that the number density of a particle is just given by the integral over the d3p, the momenta, the 3 momenta divided by 2 pi cube times the distribution function for this species. There is a question?
Sorry, Laura. Yes, I had some problems with my microphone. Yeah, I have a question regarding the last slide. Could you,
yes.
please?
Yes, sure.
Okay, so here in this range, which is called mediator freeze out. So in that regime, it means that your dark matter particle is not in thermal equilibrium?
It is.
It is, along with the mediator.
Yes. So I will understand that model. So I will, this is a very nice question. And I mean, my point is also to insist on the notion of thermal equilibrium and so on. So I will essentially answer your question in more details very soon.
Sure. Okay, thanks.
Thank you for the question. Okay, so in order to explain you everything about kinetic equilibrium and chemical equilibrium, I would like to, I mean, go back to the notion of Boltzmann equation. And the Boltzmann equation, as I said, was help you to describe the evolution of the dark matter phase space distribution, and together with it, I mean, essentially, you can look at the first momentum of the phase space distribution, so which is the integration of the phase space distribution over the 3 momenta. And so, as I was just saying before, I'm going to use this convention, n equal integration of d3pf divided by 2 pi cube. Notice that you will find many textbooks where you take the number of degrees of freedom associated to the given species out of F. Okay, I will not do that here. So this is the convention I use in case you have question compared to other textbook you would have looked at. And also just as a reference, remember that the energy density of this particle will be d3p over 2 pi cube times the energy of the particle that depends on the momenta times the distribution function of this species E. Okay, so remember, yeah. So this is the general setup, and so this is just a reminder. So as I said, I want to look at Boltzmann evolution equations. So essentially, what I'm interested in is to look at, in general, an equation that is going to connect the Liouville operator here to the collision term. just before going to what is hidden into the Liouville operator and the collision term, let me just insist maybe on something. The Liouville operator is essentially going to be influenced by the cosmology. So this is just to tell you that, I mean, just to insist, and I will maybe repeat, I hope I will repeat that. If I forget, I tell it now, that in most of, in all the lectures I'm going to give you today, I'm going to assume that my dark matter is produced in a radiation dominated era. So at early time, before matter radiation equality. This is not obligatory. So you could very well have, I mean, we only know, we have only information, precise information on the history of the universe up to BBN. We could assume, for example, that will be the cosmology of the early universe would be modified before that period. And for example, have early matter-dominated era for those who were excited by black holes. There could be like a period of the universe where it's completely dominated by primordial black holes and become radiation dominated there again. Or you could have a late inflationary period where you have also a period of early matter-dominated era. I won't have time to go through this, but if you are interested, you can ask, and I can give you some references about that. Another point is that the collision term is essentially influenced by the interaction of your dark matter with the rest of the world. So, I mean, essentially for neutrinos, we are interested by weak interactions. For my potential candidate, fermionic candidate that I mentioned before, this particle is going to I mean, the life of this particle is going to essentially be driven by the coupling lambda chi that was on the plot before. So this is essentially particle physics influenced. Okay. I will begin with the Liouville operator. Okay. And again, here in these lectures, I'm essentially going to focus on the background universe. I'm not going to discuss anything about cosmological perturbations. And when which is a super interesting topic, and I guess that it will be addressed in the next lectures. If not, again, you can ask, and I can send you back to other lecture notes or books on the topic. But I will stay with at zero order in cosmological perturbation, and I will work in Friedman-Robertson-Walker space-time, where you have the line element dt square minus a square dx square, and here you have the scale factor. So I'm considering a universe that is quite homogeneous and isotropic. And within this setup, I can essentially not have to bother about f x mu, p mu, but just simply focus on the dependence in time and in the not the direction of the momentum, but just its I'm not finding the word now. Okay. I think you understand what I mean by that. Good. So it doesn't depend on the direction of the momenta, and the energy is directly related to the length of the momenta and not to its direction. So energy is also directly into this quantity p. I will refer to the momentum length as p without any vectors on the top of it. Okay, so Liouville operator of the distribution function in this setup, where I assume that my universe is homogeneous and isotropic, can just be rewritten as E times the partial derivative of f compared to time plus df over dE over dt. I can rewrite this just simply as the Hubble rate, which is dA over dt, 1 over A. Okay. And I mean, this is exactly the point where you see what I was saying before. I mean, you directly see that within the setup we are considering here, we are working at zero order in perturbation. My Liouville operator just contain the expansion rate of the universe. And as I said before, I'm going to, in most of the lectures, in most of the lecture, consider that my expansion rate of the universe at the time of dark matter production is driven by a universe that is radiation dominated. So within this setup, I can essentially write my Hubble rate as the temperature, okay, of the bath divided by a mass scale, okay, which is, I will write it M0 maybe, and this mass scale is directly related to the Planck scale. So I mean, there is a factor 1.66 that is really directly, it's some 45 divided by 4 pi cube square root, okay? And it's, there also enters into it the number of relativistic degrees of freedom, okay? Just because this is 8 pi over 3 m Planck rho radiation. And this is the thing I should never do, because obviously there is a square root, okay, voila. It's directly related to the square root of 8 pi over 3 m Planck, and rho radiation goes as temperature to the fourth, and also has a dependency into the number of relativistic degrees of freedom. So at early times, you have many particles that are relativistic, so the number of relativistic degrees of freedom before electroweak symmetry breaking is of the order of 100, 105. But I mean, at later time, like today, for example, the number of relativistic degrees of freedom, J star, is equal to 3.36, okay? So just for the record, also, let me emphasize that when I say that the number of relativistic degrees of freedom when we are at temperature above electroweak, I'm just considering the number of degrees of freedom of the standard model here. As soon as you add up particles, you should count them and add them up. But essentially, I'm just considering very small extension of the standard model. So I would usually assume I use as an order of magnitude that J star is of order of 100 at early time, and at later time is 3.36. So I think that this is all I wanted to tell you about the expansion rate of the universe and the Liouville operator. Let me just rewrite this as energy times the total derivative per time of the distribution function. Okay, so this is this whole quantity that is hidden into here. And let me also insist maybe on one extra point, is that you might very well know that we have kind of two ways of counting the number of relativistic degrees of freedom. So J star for me will be directly related to the number of degrees of freedom that comes into the computation of the radiation density. And I will refer to HF, the number of relativistic degrees of freedom that enters into the calculation of the entropy density. So actually entropy density goes as HFT cube, again with factors of pi and 45 and 2 and so on, that I will never write because anyway, I will probably forget some p square, pi square and so on. So I mean, here we will stay with orders of magnitude. If it would be interesting for any of us, I have some handwritten notes of these lectures with all the factors written explicitly. So if you want, just send me an email and I will send them to you. Rho radiation itself goes as J star times T4. So essentially, when you count the number of relativistic degrees of freedom in general, J star T, okay, you will count them as the sum Ji rho time the temperature of a given species, because you could have a relativistic species, but which has not exactly the same temperature of the photon. This is, for example, the case of neutrino today, okay? While HF T is equal to the sum of the number of degrees of freedom of each species time I divided by T to the power 3. Okay, this is essentially why when I look at today, as I said, neutrinos and photons have not the same temperature. So this is essentially why today J star equal 3.36, while HF, the number of the relativistic degrees of freedom entering into entropy, is 3.91. They differ from each other. At early time, J star and HF are different are exactly the same, sorry. At early time, at high temperature, they are exactly the same because all the particles have exactly the same temperature. So I'm checking again if I didn't forget to tell you anything. Maybe just also for the record, so that we all, I'm sure that everybody has been introduced to the same quantity. I have written, I mean, the previous slide, there were a plot of omega. So what do we refer by, I mean, what is omega exactly? So we say the Rayleigh abundance of whatever, but omega E is the density of the particle, and this is a temperature dependent quantity, okay, divided by the critical energy density. And the critical energy density is just the one that is given by the Hubble rate, that is also a time-dependent quantity rescaled by the usual 8 pi over 3 m Planck square prefactor. Okay, so omega has no dimension. It's just a rescale energy density. If we want to account for all the dark matter today, we need omega chi h squared equal 0.12. There is this small h that comes into the game, okay, which is just some parameters that tell you what is the Hubble rate today. So you write the Hubble rate today as 100 times small h kilometer per second per megaparsec, and h equal 0.7 roughly from Planck measurement. So I hope that here I introduce you all the quantities that are going to come again in the lectures. If you have any question, if anything is unclear, please let me know now or later.
The equation in the right above the h is not a square?
Where did I write h not squared?
I mean,
sorry. You're completely right. This is what I said. I should never, I always forget the h square above. Thank you very much. Thanks. Very good, thanks. Okay, so maybe I give you a break of 5 minutes now, just to have, I don't know, you might want to have a drink or something. I personally would like to have a drink and not make too much noise. So I will give you 5 minutes now and I will continue just after. Please, if you have questions, don't hesitate to do it now. Just take just a small break now. go ahead if you have any question. Huh?
Can I have a question?
Yes, go ahead.
How did you define the Liouville operator like that way? How did you extend it?
So this is, I mean, you can really write it in a very generic way, just in a completely relativistic invariant way. So if you want, I can write you the very general way of writing the Liouville operator. Sorry, which would be LF. Whoa, sorry. So in a very general way, you should write it as the alpha, the F over the X alpha. Oh, sorry. Something happened. My lectures have disappeared. I'm sorry. Interesting. Okay. Voila. Here. Thank you. Sorry for the for going back and forth. So in very general grounds, you should very generically write it as a function of the connection, the Christoffel symbols. So you should write it like this. This would be the most general way of writing the Liouville operator. And if you go to the case where you cannot assume, I mean, you go to an homogeneous universe, you don't have a dependence of your distribution function in the position. Okay, so I don't have the df over dx where alpha is the Lorentz indices. Huh? So I just end up with a derivative per time, okay, of the distribution function times the energy, but I could very well have a dependence of df over the x, the position. And I mean, if you go to cosmological perturbation, you have to take them into account, okay? And on in the other term, you have the connection. So if you take you do the effort of computing the Christoffel symbols in Friedmann-Robertson-Walker universe, you will you will see very well that you will end up with the Hubble ray that would go out of it. And you could also have a dependency in the direction of the momenta, but we have assumed, again, homogeneous and isotropic universe. So this is why we just have the derivative of f compared to the amplitude of the momenta. Does this answer your question?
Yes, thank you.
Okay, so so I'm happy. I got a question on the 5 minutes, so I will do it again. And I will continue now with the collision term if everybody, I hope everybody is back. Okay, so I just 2 minutes ago, I was telling you I was back to the Liouville operator related to the collision term. I just told you about this part of the Boltzmann equation, where you essentially have the cosmology that enters into the game. So, but through these Christoffel symbols I was just mentioning during the break. Now, on the other side of the equation, you have the collision operator. And this is where I'm going to answer Bastian's question about, or at least I will address partially the question of Bastian about thermal equilibrium or kinetic equilibrium. Because when you work with WIMP, you directly go, yes, the collision term is related to the annihilation of dark matter and blah, blah, blah. But actually, you should be more generic than that. And you should take into account all possible elastic and inelastic interactions. So annihilation are among the inelastic interactions. It's going to change the number of dark matter particles you have in the story. But a priori, you should also take into account the fact that there are also inelastic collision. So in general, you should take into account that the collision term has a contribution from elastic collision and from inelastic collision. Whoa. Okay, so in order to go further, I will again, I'm going to assume a setup just to make things clear. And I'm just going to use the case of a particle that would have gauge interaction. That could very well be the standard model neutrino, for example, okay? And I'm going to assume that it interacts with the Z, for example, okay? So if I'm considering elastic interaction, I'm going to, for example, look at interaction of the type chi that collides over on a fermion, for example, of the standard model bath that goes to chi and a fermion of the standard model bath. So I would have, for example, this kind of interactions. Okay, I'm assuming that my chi, that would be the dark matter candidate, for example, has interaction with, for example, a Z boson. It would have a non-zero hypercharge, for example, and it could go to interact through these interactions. So here, I mean, this kind of interaction is not going to change the number of particles I have in the bath, but it's going to give rise to momentum exchange between the particle of the standard model particle and my dark matter. And in this case, I have interaction, so gauge interaction in this case, so toy model, okay? I have interaction through gauge interaction, so it's the case of the standard model neutrino, okay? So I would have elastic collision, okay, that just have a certain rate of interaction that is directly proportional to the elastic scattering cross section, which just goes as J Fermi, okay, directly entering into here. On the other hand, for inelastic collision, we go to them just after, as I said, we could have annihilation. So this is, chi-chi. That would go to fermion through the exchanges, through the exchange of AZ. Let me first focus on this part, the part of elastic collision. And just remind you, or if you were not aware of it, be careful. This is an important part of the story. So, elastic collision, inelastic, elastic collision. So if I focus on this type of interaction, so just to put them again, KF in the toy model I'm considering with a dark matter that would, for example, interact through gauge interaction, okay, with a Z. These type of interaction are going to allow to drive potentially fast momentum exchanges. And actually, when I have fast momentum exchanges, this is what allow me to assume that my dark matter or my particles in general are in thermal equilibrium or kinetic equilibrium, okay? So essentially, when the relaxation time, which is proportional to 1 over the rate of elastic collision, remember here, it goes as the Fermi constant. I have 2 insertion of the gauge coupling here, and the Fermi constant goes as the gauge coupling square. So I'm going to be able to have kinetic equilibrium or thermal equilibrium or local thermal equilibrium when the relaxation time that goes as 1 over the rate of elastic collision is much smaller than the expansion rate. I mean, the Hubble time, let's say, 1 over the expansion rate at a given temperature. So this is the condition we want to have if we want to assume kinetic equilibrium, okay? Not chemical equilibrium, but kinetic equilibrium. So the question is essentially, when do I have kinetic equilibrium, and why and how this is interesting or relevant for our discussion. So again, in this setup where I'm considering a dark matter that would be interacting with the standard model through gauge interaction, very roughly through the diagram I have shown, I'm assuming that I have a non-relativistic dark matter candidate, which is usually what you assume when you consider WIMPs, okay? You are looking at getting its relic abundance when it has become non-relativistic. I will get there right after. But assuming that your dark matter is non-relativistic, by just, looking at what is the temperature where you are going to saturate, okay, the relaxation time equal the inverse of the Hubble rate time, you can find out what is the temperature at which you are going to get out of kinetic equilibrium. And if you consider the scenario that we have, remember that tau goes as 1 over the elastic scattering rate, which itself goes at Fermi constant. So you can expect to have some Fermi constant entering into the game. So some values of the standard model SU2 left gauge coupling and the mass of the SU2 left gauge boson. You can go through the exercise, and if you want to go, please go ahead. If you want to have help to do it, just ask me, or you can look at some references I also have in my notes from Dorf and Brigman from 2006, very nicely presented there. You can extract that essentially for electroweakly interacting particle, the kinetic decoupling will happen at approximately the mass of the dark matter divided by m Planck to the power 1/4 times the mass of the Z boson, that times J-1, the SU2 gauge coupling. So if you are considering a particle of the order of 100 GeV, actually, you end up with the temperature of kinetic dark coupling, which is of the order of few MeV. Let me put few MeV. Okay. Remember that my assumption here is that my chi particle is interacting under SU2 gauge interaction. Again, we will compare this temperature of kinetic decoupling to the temperature at which the particle is expected to decouple chemically, and actually we will see that this temperature is very low. So, assuming that we are at temperature above the temperature of kinetic decoupling, we can expect that there are fast momentum exchange between the dark matter, for example, and the heat path in order to assume that they are in kinetic equilibrium, okay? And this is going to simplify a lot our life, in the sense that if I have my particle in kinetic equilibrium with the heat path, I can simplify my life in the sense that, okay, I have my Boltzmann equation that describe the evolution of the distribution function, but this distribution function depends on time and momenta. And integrating all these equations in a very general way is painful. Now, if I know that my particles are in kinetic equilibrium, I'm going to be allowed just to focus on actually the evolution of the number density. So the first moment, the integration over d3p of, sorry, now we are working with isotropic and homogeneous universe. Okay, I can just focus on the evolution of the number density of my particle, and this is really, really, really simplifying our life. No, the very nice thing is that if you have your particle that would be, for a reason or another, going a bit beyond kinetic equilibrium, but not too far from it, there has been a bunch of studies that actually tell you that you could potentially follow not only its number density, but also essentially its temperature, or a quantity that is equivalent to the temperature when you are in a thermal bath, which would be I said, okay, so yeah, you have to follow not only the number density of the particle, but also the evolution of its temperature. You really have to follow its momentum exchange. Just before, going further, let me also mention that, okay, we can focus on the evolution of number density, but even better when we want to play with Boltzmann equation and integrate out the evolution of the distribution function, we are not always going to play with the number density itself, but kind of a rescaled number density n over the entropy density. This is the comoving number density. It's a dimensionless quantity. Okay, and just, I don't know if I wrote it before, but let me just write it once for all. S, the entropy density, is this quantity that is proportional to HF T cube, and there is 2 pi square over 45 in front of it. Okay, so it's usually very convenient to work with adimensional quantities, and I will refer to the comoving number density as big Y. Okay, just for the record, if you would be a little bit beyond kinetic equilibrium, as I said, you might want to look not only to the evolution of the number density, but kind of a rescaled temperature that I will call small y, okay, which is just m chi divided by 3 times the entropy density to the power 2/3 times the momentum square divided by energy averaged over momenta. See, if you go to the non-relativistic case, you essentially can, take out here m chi divided by s to the power 2/3, 2 divided by 3, p square over 2m, okay, which might essentially remind you a notion of temperature, okay? So this is this small y that you would have to follow if you are going a bit beyond kinetic equilibrium is directly related to the temperature of your particle, if this particle would be in equilibrium with the heat bath. Here, in these lectures, I will not go through these details, but as might be introduced in the micromega, sorry, not in the micromega, but in the dark SUSY lecture, you will maybe have the opportunity to play with scenarios where you actually go a little bit beyond kinetic equilibrium, and this will allow you to play with it in some scenarios. So this is a very nice point. Another important point about kinetic decoupling is that once your particles have kinetically decoupled from the bath, okay, what happens is that they are just going to free stream. They are just going to they stream freely from anything. And free streaming might ring a bell, and maybe it's, you think, free streaming, maybe it tells you I'm talking about warm dark matter. I just want to tell you that all particles at some point, are going to go through a kinetic decoupling and actually are going to free stream and essentially erase a structure that would be that would correspond to scales that would be of the order of the free streaming scale, the scales that the particle is going to be able to freely go through, essentially. And in the case we were considering, okay, for the total model where we have a weakly interacting massive particle, actually, okay, essentially you can see that the mass of the object that you would erase due to free streaming would be of the order of 10 to the minus 6 solar masses. Okay, so so for a 100 GeV particle that is SU2 left interacting. So this is just another little point I wanted to mention, is that it's not because you have a WIMP that you don't have free streaming. You also have free streaming with a WIMP, but the point is that this free streaming happen at so small scale, so 10 to the minus 6 solar masses, is way beyond, for example, small scale galaxies that you are testing with Lyman alpha forest data, which are corresponding to mass scale of the order of 10 to the 9 solar masses. Okay, but essentially, how you are going to compute the free streaming scale is essentially ask yourself what is, I mean, everything of this discussion when you are talking about free streaming is directly related to a kinetic decoupling. Okay.
I'm sorry.
Yes.
Why the free streaming concept here is stated in terms of the mass and not instead?
Okay, because I can just, I mean, I just using the scale and assuming the typical this scale corresponds to the radius of the object I would take into account, and I just multiply the scale by the energy density typically of that matter, and I get to a mass scale. Okay.
Okay, and how does it change with the mass of the particle?
Or does it change with the mass of the particle? I mean, depends. It depends essentially what you are assuming about your particle. Okay, here I'm assuming that I have a particle that has been that which the kinetic decoupling is here. Okay. Okay. So I have the kinetic decoupling temperature here. And when I know what is the temperature of kinetic decoupling, I know essentially the moment where my particle is decoupling, okay? Mm-hmm. And so I know it's in the few MeV range. It won't change. I mean, I have m chi divided by m Planck to the power 1/4. It won't change much for a particle of 1 GeV, 100 GeV, and 1 TeV, okay? Essentially.
Sure.
So, but this is for a given choice of setup, okay? It's an electroweakly interacting particle. If I'm looking at another particle that would, for example, have completely different interaction, I would have a completely different result, okay? So the number I've given you here is just for this very rough, it's very roughly given, okay? It's not, don't take it as a religion, just redo the computation by yourself and check exactly what would be the dependence of this free streaming scale. I mean, I don't have the exact dependence here. I could provide it to you if you want, okay? But it has a dependence. Yes.
Just to clarify something, the free streaming concept here is important because this is related to the structure formation epoch, right?
Exactly. The point is that, I mean, the scales that we are considering there is not linear. I mean, there are scales which are essentially have become non-linear since a very long time, okay? So, I mean, there are many more things that just like that have happened since just the free streaming of my particle. And I mean, structure, I mean, essentially have been forming, and you cannot test essentially these scales because they have become completely non-linear. So you have structure at 10 to the minus 6 solar masses, essentially.
Mm-hmm.
You cannot test them.
Okay.
Okay.
Okay. Mm-hmm. Thanks.
Good. So, so that was for the collision term. Okay. So I remind you, I was talking about the Boltzmann equation, which relates collision term to Liouville operator. And I was telling you here that I have elastic scattering that I should take into account and inelastic scattering. From the moment I have fast enough elastic scattering, the only thing that is happening is that I can assume that my particle is in kinetic equilibrium with the rest of the plasma. And as I said, this simplifies a lot my life. First, I'm going to be able to focus only on the number density evolution of my particle, and I'm not going to have to consider higher momenta of the distribution function. I'm not going to look at its temperature or any higher momenta. But on the top of this, I can also write you what would be typically the form of the distribution function. So if the particles in kinetic equilibrium on very general ground, what you have is that you can write your distribution function for fermions or bosons as the usual Fermi-Dirac or Bose-Einstein distribution. Okay, so if I look at my dark matter particle, that would be in a kinetic equilibrium with a heat bath, I can describe the distribution function as the number of degrees of my particle, okay, the number of degrees of freedom of my particle divided by exponential of its energy minus the chemical potential divided by the temperature of the heat bath plus or minus 1. So for Bose-Einstein or Fermi-Dirac. Good. I said before that my number density and my energy density are just integrals of this distribution function times the energy or not. Just to refresh your mind, because I guess you have already seen that, but let's go to see what happened when we are in the relativistic limit and in the non-relativistic limit. So in the relativistic limit, I'm going to assume that the temperature is much higher than the mass of my particle and the chemical potential, for example. And by integrating out this distribution function, I end up with a number density, okay, that I will write like j chi n, okay, delta 3 divided by p squared times t cube, okay? So you see that the number density of my particle just goes as the temperature cube in the case where I'm in the relativistic limit. For energy density, I take the integral over this 3p divided by 2 pi cube times the energy times the energy density, and I just end up with j chi, that I will call j chi rho, okay, pi squared over 30 times temperature to the 4. So I have an n and a rho here, just because I cannot directly write the number of degrees of freedom of my particle that were here, but I actually have the number of degrees of freedom times a certain factor depending if I have a boson of a fermion. So these are the notation I'm going to use here. I'm going to write j chi n, which is actually equal to 1 times the number of degrees of freedom of chi, or 3/4 of the number of degrees of freedom of chi if I have boson of fermion. In the case of j chi rho, the prefactors are just a little bit different. In the case of fermion, it's 7/8 j chi for boson and fermions. I mean, please go ahead, integrate yourself the distribution function, and you will recover these small factors in front of the temperature cube and or the temperature to the power 4. Okay, so this is in the relativistic limit. Very simple dependence. In the case of the non-relativistic limit, so now I'm going to assume that the mass of the dark matter is sensibly higher than the temperature. In that case, I can actually write the number density as, again, the number of degrees of freedom of my particle times m chi times temperature divided by 2 pi to the power 3/2. Okay, exponential minus mk minus mu divided by temperature. So here, what you see is that you have some, dependence in 3 to the power 3/2, but very importantly, you have this Boltzmann suppression factor, and this is definitively the one that is going to win at very high temperature compared to 3 to the power 3/2. So you can, just simply here directly guess that at a very high temperature, you are going to, at very low temperature compared to the mass, you are going to have a very strong suppression of the number density of your particles. So let me just, to go one step further, introduce another convention that we are going to use here. Let me introduce you x, which is a time variable essentially. Here, for the time being, I'm going to assume that x is the mass of the dark matter divided by the temperature of the heat bath. Okay, so I'm playing with two I-dimensional quantities, which are y, the number density divided by the entropy density, and x, which is the mass of the dark matter divided by temperature. Very early time, I have a very high temperature. At later time, I have rather low temperature. So also, in order, for definitiveness, in the rest of the lecture, I will refer to the equilibrium density, the density assuming that I can neglect the chemical potential. So I'm going to say Yx, okay, is the co-moving number density of the dark matter when I can assume, I can neglect the number density, when I can neglect, I'm lost now, I don't remember what I wanted to tell you. Yes, when I neglect the chemical potential of my particle. So this is the convention I'm going to use, and that is actually used everywhere around. And when I look at this equilibrium density as a function of time, or as a function of my variable x, I can draw very roughly a plot here. Okay, I expect my equilibrium density, co-moving number density, okay, to go as, here I have, remember, n over s, okay, and we know that at early time, okay, I have number density that goes as t cubed and entropy that goes as t cubed. So this is a constant, okay? At later time, n over s is essentially completely driven by the Boltzmann suppression, and you have your equilibrium density that just gets completely suppressed at later time. Okay, so this is the evolution of my number density as a function of time. Okay, x is the equivalent of time essentially. Here is my time variable. At early time, my co-moving number density is a constant quantity. At later time, it should drop very fast as an exponential. This is what I'm going to assume, what I'm going to get if I have zero chemical potential in the story, which is not what we are going to do until the end of this lecture. Okay, just again, to fix the notations maybe, and to have a final comment on relic abundance of dark matter today. When I'm talking about the relic abundance of dark matter today, we look at the dark matter number density that I get after production, co-moving number density divided by the critical energy density today times the entropy density today times the mass of the dark matter. Okay, I'm assuming that dark matter is non-relativistic today, and this I forgot to write explicitly. Rho chi for non-relativistic dark matter particle is n chi times m chi. Okay, so if you divide rho chi by the entropy density today, this is how you end up with this expression for the relic abundance of dark matter in terms of the co-moving number density at the time of production. Okay, so this is, I think, everything I wanted to tell you about kinetic equilibrium and okay, the form of the distribution function and of the co-moving density that we are going to get. Good. So now I can go to chemical equilibrium. So or better said, inelastic scatterings. So going back to the Boltzmann equations, again, I have to change pen. I have the Liouville operator, which is equal to the collision operator. For the moment, I have been discussing the potential elastic scattering interaction that allow me or not to have a particle that is going to be in kinetic equilibrium. So I'm going to be allowed to use my standard formulas that you might know very well for particles in kinetic equilibrium or not. That's one question. On the other hand, I also have to look at inelastic contribution to this collision term. So let me go back to the case of my particle, my toy model, where I have a dark matter that interacts with the standard model particle through gauge interaction. Okay, so I go back to this case, and this is essentially the kind of diagram I'm interested in. So dark matter annihilation, which are going to essentially potentially change the number of particles I have in my bath from the moment my dark matter particle can annihilate into fermions or into any other kind of standard model particle. I'm going to assume that I'm going to be allowed to assume that my particles are in chemical equilibrium with the standard model plasma from the moment that the rate of inelastic interaction is larger than the expansion rate of the universe at a given temperature. So to know when I have chemical decoupling, I'm going to look at the moment where I saturate this inequality. So gamma inelastic equal H at the time of chemical decoupling. Okay. And as we will discuss later on, for example, within this toy model, so dark matter interacting through gauge interaction, I can actually check that my temperature for chemical decoupling is of the order of the mass of the dark matter divided by 2025 or so. Okay. And so remember what I was saying before is, I mean, when we are playing with our dark matter, when we want to compute the relic abundance of dark matter, shall we consider or not that we are in kinetic equilibrium for a weakly interacting massive particle? I usually have the temperature of chemical decoupling that is larger than the temperature of kinetic decoupling. For 100 GeV particle, you have 100 divided by 25 few GeV, while for the kinetic decoupling temperature, remember, was few MeV. Okay, so I can, for a WIMP, okay, I can usually assume that my particles are in thermal equilibrium while they are going to decouple chemically from the bath, and that I'm going to be able to go through freeze out. I will go through freeze out very soon, in a few minutes. But before going to freeze out, let me write the general form of the inelastic collision term. Okay, for that, I'm going to use, I just don't want to write it again, and especially to put a typo into it while I'm discussing. I'm sorry, I'm going through this thing very, very badly. So these are my handwritten notes. I'm just going to do as if I was having slides, and I'm just pasting now the general form of the collision term for inelastic scatterings. So this is also probably, I mean, a form you have already seen very often. I just put a 1 over E here, okay? Because here, if you remember, I had E chi times df divided by dt, and actually essentially I'm taking this 1 over E and I'm putting it on the other side of the equality here. So I'm usually going to write 1 over E times the collision term, okay? If I write this collision term, I have to take into account all possible inelastic scattering interaction, both going from a certain initial state to the production of dark matter, or from an initial state that takes into account dark matter to a final state, okay? I'm just giving some names to the state that contain dark matter and the state that doesn't contain dark matter, okay? So I take the in state that would be made of bath particle, and the final state which goes together with dark matter into the process. So I'm essentially looking at in going to fin chi, but I can have these processes going in the 2 directions, and the 2 lines into this collision term take into account the 2 possibilities. M here refer to the transition matrix element, okay? In order to get this transition matrix element, I have to go through my Lagrangian of interaction and extract all the Feynman rules. So the compact way in which I have been writing this collision term has a different quantity here. So here first I have the product of dp over 2 pi cube 2e for all the particles that would be in the initial state and the final state, okay? I'm not integrating yet over dark matter momenta, okay? I have the delta 4 here. By p fin, I'm summing over all particles in the final state, okay? And by p in, I'm summing over all momenta of the particle in the final state. This is just conservation of energy and momentum. Then in this expression, so I have two lines. In the first one, I'm going from the in state to the final state plus dark matter. I have here F in and some 1 plus minus F chi and F fin. So by F in or F fin here, I'm just taking the product. It's my way of writing the product over all the particles in the initial or final state, okay? And 1 plus minus F fin, or there is a typo here, fin, okay? F in or 1 plus or minus F fin, okay, are just also products of 1 plus F alpha, okay, where alpha are particles in the initial state and the final state. So in these parentheses, I have a product of distribution functions of the particle in my initial state in the first line, or a product of particles in the final state times the distribution function of dark matter, multiplied by these 1 plus minus F factors. And these 1 plus minus F factors are related to spin statistics. So you call them poly-blocking factors or Bose-Einstein enhancement factors. Poly-blocking for fermionic dark matter, it comes with the minus sign. Bose-Einstein enhancement comes with the plus sign. These factors can have an effect on essentially the relic abundance of your dark matter. Here, for simplicity, I'm going to essentially assume that I can neglect this contribution. I'm going just to assume that this is true. Let me emphasize that, for example, there has been a nice study. I mean, I guess there are many, but there has been a study where, for example, you can check in the Micromegas manual on freezing that actually these factors can essentially potentially affect the freezing relic abandon. So you should be careful when you neglect these kind of terms. But this is what I'm going to assume for the rest of the lectures. I'm also going to assume that, so essentially I'm going to assume that 1 plus or minus f fin, 1 plus minus f in, and 1 plus minus f chi, depending if chi is a scalar or fermion, are equal to 1. Okay, so I'm just going to take these factors to 1. This is one assumption. A second assumption is that I'm going to assume CP invariance. Not writing the same in the right way, but okay. I'm going to assume that there is CP is invariant. So I'm going just to refer to m square, the amplitude square summed over, I mean, amplitude square summed over initial and final state. So there is absolutely no averaging here. In going to fin plus chi equal m square fin plus chi going to in are just simply equal. Okay. So this is these are the assumptions I'm going to do for the rest of the lectures. And in this setup, I can actually simplify a bit the form of this overall collision term for inelastic interaction. So I can go back to write it by hand. Okay, I have 1 over 2 e chi, the integral over the momenta of all particles in the initial and final state, except for the dark matter. Okay, alpha is not a Lorentz index, but it just runs over all the particles. 2 by 4 times delta 4 that ensure conservation of energy and momentum times amplitude square once for all times f in minus f fin times f chi. So this is the, let's say, simplified version of the Boltzmann equation that I'm going to consider for the rest of the lectures of this morning and this afternoon. Good. So this is essentially everything I wanted to tell you about chemical equilibrium and kinetic equilibrium. And I mean, for the moment, I will go back to chemical equilibrium and about Boltzmann equation until now. I don't know if there is any question before I go to the standard freeze out, let's say the textbook production mechanism for dark matter. Any question?
Is the integration measure okay?
Sorry?
How can you, the integration measure in the equation above?
What do you mean about integration method?
dp should be cubed or no?
Oh, you're right. Thank you. Yes. It's over the 3 momenta. Thank you very much. Any other question? Okay, good. So now I can go to the freeze out mechanism. And essentially here, what I'm going to do is to, let me go back to the picture of the neutrino. Here, for a moment, we are just going to consider essentially the neutrino. So I copy this and I just go back to this picture. So my point is to discuss freeze out. Okay. And I essentially want first to discuss how I get this point here and how I get that point here, and I will also mention that point. So what is the difference? So, I mean, in the case of the neutrino left, the standard model neutrino, I have SU2 left interaction for my neutrino with the standard model heat path. So I can essentially assume that, I mean, when I'm following the evolution of my number of particles, and I mean, in the very early universe, they were in chemical and kinetic equilibrium. But at some point, it might be that, I mean, these weak interactions are not going to allow my particle to stay in chemical equilibrium, even though it will go out of chemical equilibrium, as we have seen. Kinetic decoupling happen much later. So actually they will continue to be in kinetic equilibrium, but they will decouple chemically from the bath. And at the point where they will decouple chemically from the bath, we will get the freeze out. So the comoving number density is going to become constant. So about freeze out, I have essentially two possibilities. So let me just to say that what I'm going to try to get now is a moment where the rate of inelastic interaction, so here will be the annihilation of my dark matter, that is the standard model neutrino, into standard model fermions. And I'm going to look at what is happening when I'm just getting to a chemical decoupling. And in order to know what is happening there, I have to essentially look at the neutrino interactions, which depend on the gauge coupling, and depending on what I'm going to assume, if the dark matter here, the neutrino, is relativistic or non-relativistic at the time of chemical decoupling, I'm going to have one or another solution here. So let me go to the first situation where I will have, let's say, a hot relic. By hot relic, I just mean a particle that decouple chemically from the heat bath when it is relativistic. Okay, so in this case, if I go back to the picture I had before, I have my co-moving number density as a function of time, while the particle is relativistic. It's essentially a constant, and if it can continue to be in fast interaction, in elastic interaction with the thermal bath, it will follow the equilibrium curve up until the end and get, I mean, Boltzmann suppressed today. Now, if the particle decouples while it's still relativistic, it decouples in the situation where we are here. Okay, so it's very easy to estimate what is the relic abundance of my dark matter at the time of production, or let's say at the time of decoupling. So I would have, let's say, kinetic decoupling that would happen at this temperature. So remember, X is m chi divided by T, by the temperature. Okay, I can very easily, with the tools I gave you before, very easily estimate what is the co-moving number density of my particle at the time it decouples chemically, assuming that it decouples chemically while it's non-relativistic. And I will show you the example of the neutrino, but let me first give you the result. I mean, this is number density when it's chemically decoupled divided by entropy density. Okay, remember that number density depends on the number of degrees of freedom of my particle that enters into the number density, and the entropy density is nothing but temperature cube times this number of relativistic degrees of freedom that contributes to the entropy density. So in the case actually of dark matter that would be in thermal and chemical equilibrium early on with the plasma, like electroweakly interacting particles, and that will decouple while it's still relativistic, I end up with a very easy way to compute the Rayleigh abundance, just some number that end up with like 0.28, so factors of pi and so on, times the number of degrees of freedom contributing to the number density. So this is just the number of degrees of freedom of the particle times 1, or 3/4 if it's a fermion, divided by the number of relativistic degrees of freedom at the time of chemical decoupling of my particle. So you really see that essentially the interactions that my particles have with the plasma only enter into the temperature of chemical decoupling here. Okay. So let me go to the case of essentially the standard model neutrino, which is the case where I have J chi n, which is 3/4 because it's a fermion times 2 for the number of degrees of freedom. And let's now see what is the temperature of kinetic decoupling I could have for such a particle. So for this, I have to estimate what is the typical annihilation rate of my particle, okay, which is of the order of its annihilation cross-section times the number density. I'm assuming that my particle is still relativistic at the time it's interacting. So number density essentially goes as T cube, okay? And I expect, because my particle is interacting with gauge boson, okay, I should have the J square coupling of SU2, okay, entering into the game. So I expect a J square dependence, or equivalently, that sigma V should go as JF, the Fermi constant. And in order to have the dimension right, I need a T square here entering into the game. So essentially here, I end up with JF T5 annihilation rate, okay? And in order to find out what is the temperature of chemical decoupling, I need gamma annihilation equal to the Hubble rate at the time of chemical decoupling, which is nothing but, as you might remember, temperature squared divided by m0, which is essentially the Planck mass up to the number of relativistic degrees of freedom and a factor of 1.66, okay? If you do your maths, you will end up with the temperature of chemical decoupling of such a particle to be of the order of MeV, okay? And what is the use of determining this temperature is essentially to determine what is the number of relativistic degrees of freedom that are in the bath at that point, okay? We have photons, okay? We have electrons, okay? The GO is, again, I mean, you have the contribution that comes with a factor of 7/8 or factor 1 if it's a boson, okay? Plus 3 neutrinos for 3 generation. And this is 10.75. If you go back to your equation here, and you put these numbers into the game, you get y chi infinity. And if you get y chi infinity, you get, I mean, the number density at production. I don't remember how I wrote it, if it's production. And then I can get the Rayleigh abundance just by multiplying by the mass of the particle, assuming that it has become non-relativistic in between the time it was relativistic and it decoupled and today, okay? I can just get it from multiplying the co-moving number density by the entropy density, the mass of the particle, and divide by the critical energy density. And at the end of the day, I get to this, let's say, I guess, famous formula that you have probably seen in very many occasions, that the relic abundance is nothing but the mass of these particles, the neutrinos of the standard model in this case, divided by 92 electron volt times, okay, Jk divided by 2. If Jk is different from 2, you don't have 92 electron volts. So this is valid for a hot relic, so a particle that they couple chemically from the plasma while it was non-relativistic and interact with the plasma through electroweak interaction. So this is exactly the case of the standard model neutrino. The usual bond you extract from it is that in order to have omega chi h square smaller than 1, okay, you need your masses to be smaller than 92 electron volts. We don't want, so this is, sorry, just for a record, Coswick McClelland bound. Now, what you want at the end of the day is omega chi h square equal 0.12, which tells you essentially that if you would like to have all the dark matter in the form of standard model neutrino, which would have decoupled while it was still relativistic, and you don't know anything about your neutrinos, you would need to have the total mass to be smaller than 10 electron volt. Equal to 10 electron volt, or 9.2 electron volt. And as I said at the very beginning, we have already a bunch of information about masses of neutrinos, and we know that, so in general, it could be possible for any beast, maybe, but in the case of chi equal neutrino left, we can definitively not have 10 electron volts total mass here. So this tells us, this essentially have given the result of what is happening, how we get this point here. The dark matter is a hot relic. Just to add up, you see here that, excuse me, small bug. So here you see that your relic abundance is directly proportional to the mass of the dark matter in this story. So you recover directly this dependency, omega chi h square, just proportional to m chi. You see that from, small masses going to a certain critical mass. Here, let's say you have really your relic abundance that just grows with the mass of the neutrinos. So now it's a moment where I would like to go to a cold relic dark matter, but I won't have the time to go through the details of the computation, in particular of the Boltzmann equation. I think I will, introduce the story for a few minutes, and we will go back to it this afternoon. So now our point is to introduce the case of cold relics.
I have a question regarding
Yes, sure,
this.
go ahead. Sorry, I didn't ask.
So I'm a little confused. Can you back to the previous slide?
Sure.
Because you, in order to get, you said this condition of the annihilation rates must be equal to this Hubble rate in order to get the temperature. So, what is the condition that must to occur in order to determine this maximum value for the mass of the neutrino? Because in the plot that you show the relic abundance as in terms of the mass, you have this maximum. But my question is, what determines that point?
What determines that point? I mean, notice that this is a very large value, right? You have definitely your particle that is largely overclosing the universe. Everything that is here above doesn't make any sense, huh? Okay? Essentially, okay?
Correct.
Now, what drives this maximum there, which is written there, is essentially the dependence of your annihilation cross section as a function of the mass of your dark matter versus the temperature that is in the universe. So, if you want, essentially here, I'm driven by the idea that dark matter, okay, decouple chemically while still relativistic. Okay, so essentially I'm assuming that my particle is still relativistic. So if you think in terms of cross section or number density, you have seen that I'm assuming that the number density goes as T cube, okay, which is not the case if I'm non-relativistic. So I go back to here, what I was saying before. When my particle is relativistic, I have this number density that goes like that. If my particle is non-relativistic, this is what we will see later, I have a different dependency, okay? And I also have the annihilation cross-section. Essentially, I have gauge interaction, but if I'm assuming that the main, let's say, the main energy dependence, okay, comes from either at very high temperature in the annihilation cross-section, what is the main energy input is the temperature, okay? When you consider non-relativistic particles, it's not anymore going to be the temperature, which is going to be negligible, and you have other quantity that comes into the game, okay? Like the mass of the dark matter or the mass of the gauge bosons. So here, up until now, I have only described this part of the plot, okay? And essentially when I cannot anymore assume that my particle decouples while it's still relativistic from the, I mean, goes through chemical decoupling while it's still relativistic, I enter into, let's say, this part of the story. Okay?
Yes, but I mean, beyond the point that above the dashed line, it's not non-physical region. In principle, when you solve this equation above, in order to determine this this temperature, in principle, you can have a relativistic decoupling with a neutrino with mass 10 GeV, for instance, or that's not possible.
It's possible, but it will have a higher relic abundance.
Yeah. That is my point. So
yes,
you are cutting off in some way because you are saying that is not a physical
it will overclose
region.
the universe. Yes.
Yeah. Okay. Thank you.
But if you assume that your party, I mean, so exactly, you will overclose the universe.
Okay.
So I can draw the line, but essentially it doesn't really, I mean, this is the Kausik, I'm sorry, I cannot say that, Kausik-McClellan bound, essentially. The one I drew before. Okay, everything above is essentially overclosing your universe, so you don't want to go there. Yeah, sure. And probably I should only, draw it in the region where it makes sense to consider it, so where my particle is still relativistic at the time of decoupling. Okay?
Okay.
Does this make sense?
Yeah, yes. Thanks.
Okay. Is there any other question? I guess I should leave the floor now.
Yes, Laura, sorry about that. It's 12 already. And
sure.
To finish 15 minutes ago, but I decided that...
Oh, You should
No,
have
no, but
told me.
it's totally fine. It's totally fine that you got some more minutes. It's totally fine. We were thinking already about that, so no
Oh,
problem.
I'm really sorry. I didn't realize. I thought it wasn't at 12, but I would have thought before. I mean,
I saw you very excited about that, and I saw that there were also questions, so I didn't want to mention and to interrupt. So,
Oh,
so
yeah.
no problem at all. But I think we should probably go to the coffee break if that's okay with you, Laura.
Sure, absolutely.
Okay. In any case, I know that you have a second lesson, a second
Yes,
session
yes.
in the afternoon, so maybe you can just continue there with all this stuff. So that would be totally fine.
Sure, absolutely. I mean, that was the point. Yeah.
Okay, very good. Thank you so much. Well, in any case, students, if you have any further questions for Laura, you are more than welcome to also to look for her in Gather Town. That would be, I think, ideal. And just continue the discussions there.
You can also send me emails while yeah, I didn't give you the time, but if you have any question, please you can also send me an email in between. Huh? So here is my email address.
Very good. Thank you, Laura. Thank you. Okay, so let's stop here for 15 minutes. Okay, we will resume at 12:15. And I think next one speaker will be Jesus Zavala with cosmological stuff, with more astro. So yes, let's break here. Let's take a coffee and come back at 12:15. Thank you. See you.
Thanks.